Yesterday was kind of a long video. Today we have quite a bit to go over, but probably will not be as long because some of these things are things that we can just, use a calculator for or find the algebra really quickly. And again, we're not done with the section, so you can't, go to the learning objectives and finish all of those off and say, hey, after the lesson, I think I'm at. But we're still setting up models to represent real-world phenomena, and this is our objective, numerically, algebraically, graphically. We're going to combine algebraical, graphical, and numerical methods to solve and verify solutions. We're going to use the problem-solving process to model and solve real-world applications. And we want to understand some of the limitations of the graphical method, and that piece will probably be more for tomorrow. But we're using the problem-solving process all through these. So this one says let's combine some methods. We're going to solve an equation algebraically, and then we're going to verify that piece graphically. And I'm going to go ahead and darken that graph. It's just too light. All right, so what we want to do is just the math that we have known for a long time, which would be to solve this algebraically. We take a look at it, we see that it's a cubic, and we think, well, all right, well, all I can really try is factoring. But to factor and solve, I need to have a 0 on one side. So I'm going to have to subtract 11x squared and 10x from both sides. And as I'm doing that, I'm realizing, hey, those all have an x. I'm going to be able to factor an x out of there. Looks like so. Hey, let's take the x and anything else that we could possibly take, but with 6, 11, and 10, there's no other common monomial factor. So we'll take the x, and then we will hope that we can find something factorable out of this. And if you were worried it's not going to be factorable, I'll have to complete the square. You could always do b squared minus 4ac, see if it comes out to be a perfect square. In this instance, it will. So let's try some combos here. 6 in the front, 1 and 6, 6 and 1, 3 and 2, 2 and 3. And then in the back for the negative 10, negative 1 and 10, 1 and negative 10. Probably not one of those. Negative 2 and 5, positive 2 and negative 5. And then I always remember that the book writers, of course, are mathematicians. So a lot of times they'll have it be the last combination that we would write down. So I start looking at the bottom here, and I've got outside times outside is negative 10, inside times inside is 6, so that's not it. Negative 5 times negative 3 would be negative 15. 2 times 2 is 4, and there it is. So we'll have x, but in the parentheses, our first numbers have to be a 3x and a 2x because those have to multiply to the 6x squared. And in the back, we need the plus 2 and the minus 5 because that has to multiply to the negative 10 that we need in the back. But outside times outside plus inside times inside is always a really good check to make sure that middle is still working. Negative 15 plus 4, boom, there it is. So here, we'll have a 0 at x equals 0. With this one, again, if you just set it up, you're going to go, oh, x equals negative 2/3. And I'd have to subtract 2 and divide by 3. And then 2x minus 5 equals 0. I'd have to add 5 and divide by 2. X equals 5/2. So that's where our zeros are going to be at. So graphically, we know we're going to see one there. Negative 2/3 really close to that one, and then 2.5 about there. Now, here's the other thing that we know. We know that this came to us as a cubic with a positive first term. So that tells us that the end behavior will be like so. Now, it might not be quite so dramatic, but it will be something very similar to that. So now what we would do is we'd grab the graphing calculator and put it in as we solved it, as it were 0, and then use the calculator to finish it up. Because if this is a test question, we want to know all the absolutely... All right, where's my calculator at? All right, my computer just did a spaz there for a second. I'm going to hope that everything is going to be fine. We had 6x cubed minus 11x squared minus 10x. 6x to the third, pop it out, minus 11x squared minus 10x. And zoom 6 for a negative 10 to 10 window. Yeah, that matches. But what I need to do is figure out what is this top point right here. And then I'm going to need to see where is that lowest point down there. So I'm going to have to change my window so I can see more of those y values, the lower values. So let me try negative 20 and see if that's enough. Hit graph. Just enough. Just enough. All right, so let's find, I need to go back to quit here and try the graph. So second trace, number 4, maximum. Oh, Blinky's already on the left on mine. I hit enter, and then to the right of the hill has to be going down. Enter, enter through guess, and there's our maximum there. So let's write that one down. We've got a local max of negative 0.353 and 1.895. So that's a local max. And then on the other side, we have a local min. So let's get Blinky busy again. Second trace, number 3. This time I've got to get Blinky on the left side of the valley and press enter. And then the right side of the valley and press enter and enter through guess. And Blinky tells us that will be 1.575, rounding to 3 decimal places, negative 19.595. Now, what we saw when we had to change the window is that for the y's, we're not going to be able to go by 1. So I need to do some labeling here, 1, 2, 3, 4, 5, to show people I did continue on by 1s with my x's. But for my y's, I can't do that. I needed to get to that 19, that negative 19. So I need to maybe go by 2s, 2, 4, 6, 8, 10, 12, 13, 12, 14, 16, 18, there's 20, and then negative 2, 4, 6, 8, negative 10, negative 20. So that's very obvious to somebody looking at it what we're trying to do. And then we would use that local max and local min piece to write down our point at negative 0.353 and almost 2. Maybe right there, and then it came down and hit 0, and then 1.575, almost negative, a little more than negative 19 and a half. 1.575. Out there. And we have it. So yes, on a test, what we were really looking for was where are the solutions, but we want to be able to put this together and get the whole picture of the graph. And without calculus, we can't find those local maxes and local mins by hand, so we have to use the graphing calculator for that. And everything fits. Like I said, it's verified graphically. And you always make sure that everything that you need about your answer can fit on your graph. That means sometimes you will have to change your intervals to make that happen. If it doesn't fit, then you're going to lose mega points. You have to think about that, analyze the situation beforehand, and tell yourself, hey, this isn't big enough, I need to fix this. Now, the next one says we need to solve this equation, and we want to solve it algebraically again, and then put that together with the graphical, because part of our objective was using different methods at the same time. So again, we see, hey, it's got an x squared. A degree 2 polynomial is quadratic. Factoring, that's what I would try. So I'm going to have to add 4x and subtract 10 from both sides. And then, of course, I would try factoring. So there's no greatest common monomial factor. It is not a perfect square trinomial with a negative 10 in the back. I need to find two numbers that multiply to negative 10 and add to 4. Negative 1 and 10, 1 and negative 10, negative 2 and 5, 2 and negative 5. Wait a second, that's not working. And that's because it's not factorable. Now again, you can do b squared minus 4ac It's only factorable if that comes out to be a perfect square. So this one would be 4 squared minus 4 times 1 times negative 10. So 16 plus 40, and that's going to be 56, and that's not a perfect square. So we know we're right, it's not factorable. So next line of defense would be complete the square, and this one won't be so bad because it has a 1 in front of the x squared, and it has an even b value. So let's move the 10 over, and then let's complete the square. So again, you think of that little b over 2 squared, and that's going to be 4 divided by 2 squared, which is 2 squared, which is 4. And so we're going to add 4 to both sides. We're going to get 14 on the right-hand side, and then we think, well, what did we square to get the 4? We squared a 2. Now, we would go ahead and take the square root of both sides, and as we're writing that square root down, we should be thinking to ourselves, oh, whenever I physically make that motion for a square root, I have to do the plus or minus piece. Then I try to think, 14, any way to simplify the square root of 14? So I run through my perfect squares, 4, 9, nope, not going to go in there. So to leave it perfect, I'd leave it the square root of 14. But I still have that negative 2 to move over. So negative 2 plus or minus the square root of 14. So we subtract 2 to get rid of that plus 2. Now, those are numbers we are not going to recognize if we use a graphing calculator to get this, because they're going to be nasty decimals. So what we would do is we'd grab our calculator, and I'm just going to use my handheld one here, and we would punch in negative 2 minus the square root of 14. And that will give us negative 5.7416. So negative 5.742. So there is one of our zeros. And then if I do second, enter, and then I just change it to negative 2 plus, so all I'm doing is changing the plus symbol there, I'll get 1.741657, blah, 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 so 1.742. So again, those would not have been something we would have recognized, and we would know, oh yeah, then this isn't something that I can factor because it's not coming out as a nice rational number, a fraction. So there are our 2 zeros. Let's put those on our graph. So negative 5.742, 1, 2, 3, 4, 5, about right there. And then x equals 1.742, somewhere over there. But I'm not going to put my intervals on yet. Obviously, my x's I can go by ones, so I could put those on there. But usually I'll just wait and do it at one time because I need to see, what does this look like? Should I go by a different interval when I'm going to figure out what my y's need to be? So x squared plus 4x minus 10, good chance that we'll be able to fit that one on there as you look at the numbers. But let's take a peek at it. All right, so that was our x squared plus 4x minus 10. I'm just using the zoom. I think I still have that set from the last example. So we can't go by ones. Look at that. Let's change our window. And maybe we'll try, might as well go with negative 20, huh? And we could go by twos. Hit graph. Yep, there it is. So let's find that local minimum. Second trace. And number 3. And Blinky's going to help us out here. We'll use our left arrow to go to the left side of the valley. We're coming up. Hit enter. And then use the right arrow to go to the right side of the valley. Hit enter. Enter through guess. Oh, really super close to negative 2, negative 14. In fact, with our rounding to 3 decimal places, it's going to be negative 2, negative 14. Now, in fact, that part we could do algebraically if we remembered our little formula from way back in exponential for figuring out what the vertex is. And that little formula for finding the vertex is that x equals negative b over 2a. Well, we've got a 4 here, so it will be negative 4 over 2 times 1, which is -2. So what Blinky just did when we were asking to figure out what that minimum was calculus. And so it was just a teensy bit off, and we saw that. But if we put the -2 back into the equation, then we can figure out what the y value is. And for this one, we'd have -2 squared is 4. 4 times -2 is -8. So 4 minus 8 is -4, and -4 minus 10 is -14. So again, 2, 4, 6, 8, 10, and 20. 2, 4, 6, 8, -10, and -20. But 1, 2, 3, 4, 5, and 10, and maybe 1, 2, 3, 4, 5. We'll label our negatives as well this time. So we have our zeros. We just have to put our -2 and -14. 2, 4, 6, 8, 10, 12, 14. There we are. And again, we made it so that it fits on the graph. You can't start adding new grid or anything like that. That's considered really amateurish and immature when you get to the college level. So we always make sure that we change our intervals to make everything fit. Now, while the decimal answers are certainly accurate enough for all practical purposes, it is important to note that only the expressions found by we did completing the square, not the quadratic formula. You get the same answers anyway, so by completing the square, CTS, they give the exact real number answers. And that's what we want at this level. Most of the time, we want to have those perfect answers, but the realization that if we need it for the real world is that we're probably going to have to round it. So the tidiness of exact answers is a worthy mathematical goal. Absolutely it is. And that's what we spend most of our time doing in here. Realistically, however, exact answers are often impossible to obtain, even with the most sophisticated mathematical tools. So, perfect is hard to get in the real world. Now, I'm going to have a couple of boxes here, which tells us we've got a summary of information coming up of good things that we could use. So every method of solving an equation usually comes down to finding where an expression equals 0, because those are the solutions. If we use f of x to denote an algebraic expression in the variable x, the connections are as follows. So the fundamental connection is when we are trying to find where f of x equals 0, we have lots of names for doing the exact same thing. The root is the solution of the equation. It is also called the zero. Zeros graphically are the x-intercepts of the graph. So all of those things are basically using the same math, but we have different vocabulary to describe the situation of what we're using it for. With word problems, we're probably looking for the solution. Graphically, we're looking for those x-intercepts. So like it says, note that functions in two variables have zeros. One variable equations have roots. And those are situations where we're solving something like this. And we'd add 7 to both sides and then take the square root. So depends on what you're working with too, the vocabulary that you should use. A problem-solving process. Word problems. First, understand the problem. What on earth are they asking you to do? And I've found over the years, and you're going to have a lot of methods here that I'm going to read through as we go through this. The thing that works easiest and best for most students is to always start with a total and then work your way backwards. That seems to help when you get to very involved word problems. Sometimes they're so easy that you just know how to set it up when you're reading through it. Read the problem as stated several times if necessary. What are you looking for? What do you have? What's the unknown? What's the total? Be sure you understand the meaning of each term used. If you see a label or something that you have never worked with before, Google it. Take a peek. What is it? One of the big ones has to do with energy. Ohms. I don't have a clue what an ohm is, and look it up and get a feel for what is an ohm. Restate the problem in your own words. Discuss the problem with others if you can. The more you can think through it, the better. Identify clearly the information that you need to solve the problem. How are you going to get there? Find the information you need in the given data. What pieces of the puzzle did they give you? Step 2, develop a mathematical model of the problem. So absolutely draw a picture. Anything geometry worthy, anything about shapes, draw a picture, visualize the problem situation. It usually helps. I mean, almost always. Introduce a variable to represent the quantity you seek. What are you looking for? What are you supposed to find? So in some cases, there may be more than one. Use the statement of the problem to find an equation or inequality that relates the variables you seek to quantities that you know. So use the information to go forward. Step 3, solve it. Once you have a model, we know how to solve a lot of different mathematical models at this point. We've been talking about algebraically, numerically, graphically. So like it says, support, confirm the solution, check it, solve algebraically using traditional algebraic methods, and support it graphically or support it numerically using a graphing utility. Again, this book doesn't say graphing calculator. That's what we're going to use. Solve graphically or numerically using a graphing utility, and confirm algebraically using traditional algebraic methods. You're having trouble finding it? Sometimes you can work backwards. Sometimes you can get the answer and then figure out how that math would set up. Solving graphically or numerically because there's no other way possible. So you grab your graphing calculator and you can find a solution that way, and there's no other way for you to go about it, then that's what you do. When we start getting into some quadratics, we know already we have to use completing the square to solve those. We're going to run into situations where we might not be able to factor a cubic. Definitely when we get into quartic territory and quintic territory, yeah, it becomes a, oh boy, I've got to use my graphing calculator because I can't figure out how to factor this. Then, interpret the solution in a problem setting. Translate your mathematical result into the problem setting and decide whether the result makes sense. That's a step that usually gets skipped, and it shouldn't be. What you found, does it make sense in the given situation, is important, and it's really valuable. It's a valuable skill. So applying the problem-solving process. The engineers at an auto manufacturer pay students 8 cents per mile plus $25 per day to road test their new vehicles. So they're just driving around, checking it out. A says, how much did the auto manufacturer pay Sally to drive 440 miles in one day? And then B says, John earned $93 test driving a new car in one day. How far did he drive? So as I'm thinking about this problem, I'm thinking in terms of a total. And a total for Sally and John would be, how much money did you make? And to make that money, I think, all right, how'd they get that total? Well, they earned $25 per day plus the rest of it depended on how much driving they did, because it was 8 cents per mile. So what I would want to do is ask myself, what am I really looking for here, and what's my variable going to stand for? And since it was miles, I think I'm going to use M for the miles. Now, if I want this as a function, I could certainly change this up a little bit and say C stands for the cost to the company, and that would give me another variable to work with instead of the T for total all the time, because again, you kind of want your variables in word problems to stand for something that matches what's going on with the problem. And then it says set up the model, which really did by thinking about the total. The cost, and the cost to the company is going to be determined by the number of miles, $25 per day plus 8 cents per mile. So there's our model, and it's in a function. This one, if we go back and read the problem, we don't see anywhere that it said that it had to be a function, so we could just use a variable like y. But it's nice to have that link between cost and miles. Now, A, how much did Sally get paid if she drove 440 miles in one day? So again, that cost of $25 per day is already taken care of. So I think, all right, Sally, you went 440 miles, huh? So that would mean you're going to have 25 plus 0.08 times 440. And then, of course, we could just punch that into the calculator. And what we're really trying to find is, for the cost for the company, if she goes 440 miles, what does she get paid? And that's going to be $60.20. Then B said that John earned $93 test driving a new car in one day, and maybe he forgot how far he was driving, so he wants to take a peek and figure that out. So 93 would equal 25 plus 0.08 m. We would subtract the 25 from both sides, just solving it. Divide by the 0.08. And grab a calculator, and it would come out to 850. So 850 miles. We want to put those labels on there so that our answers will make sense. Now I think about it, and Sally only drove 440 miles. She made $60.20. John drove 850 miles and earned $93. Well, that makes sense. I mean, he drove more, so he should make more money. So you stop and think, does this match with what I know? Now, we could certainly put our equation into the calculator. We can see that our 8 cents per mile, that's our slope, because this is in front of the m, which would normally be the x variable in our y equals mx plus b, and it would start at 25. So like I said, we could quickly come up with those graphical representations, and we could see in the graph for Sally, we've got that 60.2 and 440. And for John, we have the 93 and 850. Looks like my line isn't quite, my horizontal line over there isn't quite straight. But, pardon me, that absolutely verifies what it was that we had algebraically. And again, that's what this section is about. Our objectives are about. So then, interpret. Sally wanted to know how much she earned. Sally earned $60.20 for driving 440 miles in one day. Brings together all of the really important numerical pieces of the problem. And then for John, he was trying to figure out, well, how far did I drive if I got $93? So John earned $93 for driving, and his was 850 miles in one day. So with this one, they could switch this up and make it a little harder if all of a sudden they weren't just there for one day. You know, then we would have more variables involved in this problem. But this one was pretty straightforward. The next one, we're going to have to be on our toes for. Extra examples. We've got a jet. A jet flew from New York to Los Angeles, a distance of 4,200 kilometers. The speed for the return trip along the same route was 100 kilometers per hour faster than the outbound speed. If the total trip took 13 hours, what was the jet's speed from New York to LA? Now, we've got a little reminder over here in the blue. Distance equals rate times time. And our model says to start with identifying the variable. But what I want to do with you is come up with a method for this. You know, what is it exactly that we want to do? And to start, I'm going to ask you to find me a total. So I want you to read through that problem and see if you can find a total. Now, most people will look at this and say, well, the last sentence says the total trip took 13 hours. Now, that's what's important about the setup of this problem, because what you just decided was that this problem is going to be about hours. So we're going to need hours for one of the routes, hours for the next route, and it has to add up to 13. So it's about time. And I look at our distance equals rate times time, and I realize, well, if distance equals rate times time, and my equation has to be about time, I better solve that for t. So I better divide both sides by r, and it's going to be distance divided by rate equals time. So we have some distance that's going to be divided by some rate for the first, like it says, we've got the trip outbound and then back. That plus the second distance and divided by the second rate, that will give me the first time plus the second time equals a time of 13 hours. Now that's only one way to set this up. It totally has to do with when you read through that problem, what grabbed you as the total. This is actually going to be the easiest way to set it up as well. So the first thing I'm looking for is a jet flew from New York to Los Angeles, a distance of 4,200 kilometers. There is distance 1 right there. The speed for the return trip along the same route was 100 kilometers per hour faster than the outbound speed. And I realize, well, I don't know what the first speed was. I don't know what that is. So I could leave that as r sub 1 to stand for rate, or I could change it to x. I think I'm going to stick with r sub 1. So r sub 1 is going to be speed of first trip. Now I really don't want any more variables, so I want to try and use that one for the rest of this equation. So there's the first trip. I need the second trip to add to that to give me the 13. And it said the speed for the return trip, and I realized, oh, it's exactly the same distance. That's 4,200. So now I just need to know, did they go faster? Did they go slower? What happened there? And I see the speed for the return trip along the same route was 100 kilometers faster than the original. Well, remember, the first trip was r sub 1. So this is going to be r sub 1 plus 100. All right. So I have myself a very nice looking equation here, and I know I'm going to need some more space, so let me rewrite this down here. All right, and we have done this before. We have solved fractions like this before, and if, like I said, if you want to change it to x because you'd rather have x's than r sub 1's, go for it. But what we have to do is we have to find the LCD and multiply the entire thing by the LCD. And my LCD has to have everything there and to its highest power. So I'm going to have an r sub 1, and I'm going to have an r sub 1 plus 100. Now, 13 over there is 13 over 1. And adding a 1 to my LCD is not going to make any difference. So it's those two pieces that I need. So each one of these three terms needs r sub 1 and r sub 1 plus 100. So all three. All right. Good news is, the first two terms here, we're going to see a little bit of canceling. This r sub 1 is gone. So this is going to be 4,200 times r sub 1 plus 100. And yes, I just went ahead and switched around that multiplication because multiplication is commutative. I'd rather distribute the 4,200 than work backwards. Okay, so on the second one, the r sub 1 plus 100 is going to cancel out, and we'll get 4,200 r sub 1. Now, on the back here, we're going to go ahead and distribute 13 r sub 1 through our parentheses, and that'll give us 13 r sub 1 squared plus 1,300 r sub 1. So now I take a look at it, and I think, all right, I need to get rid of my parentheses, and that means I'm going to have to distribute the 4,200. So we add 2 more zeros to 4,200 and it becomes 420,000. And now we would want to put our like terms together. You know, over there on the left-hand side, we see that we had 4,200 R sub 1 and 4,200 R sub 1. So 8,400 R sub 1 plus 420,000. And then I recognize that my polynomial here, my equation, is going to be a quadratic because the highest power that I see for my variable is a 2. And the way that we typically try to solve those is by factoring. So what we would want to do is move everything over to one side. And I like to keep my squared term positive, so I would leave that one there. So we'd have the 1,300R minus the 8,400R, which would be negative 7,100 R sub 1. I dropped my R sub 1 there. And minus 420,000. All right. So now, this one is not going to be fun to factor. It's usually one of those things where if I give students a little bit of time, they can find it. And maybe you might not think it's factorable, so one of the things you would want to do is an educated cheat. So let's go ahead and put this into the graphing calculator because we talked about that. That's one of the ways that you can solve problems is use all of the methods together to figure out what's going on. So y equals, we had 13x squared minus 7,100x, and then it was minus 420,000. All right, huge numbers. So window-wise, our x's, that was our rate, our speed, and this is a plane, so that could be pretty big. Let's try 1,000. And our y values, well, our last number down there is a negative 420,000, so that could be really large too. So let's try negative 200,000 to positive 200,000 and graph. There is our solution. So if we can get Blinky to tell us what that spot is, we can work backwards. Second, trace, and that's a 0. So I'm looking at where Blinky says it is. It says it's down here or up here at 500, negative 720,000. It's down there with that negative 720,000. So I'm going to try and bring it up with the right arrow. And actually, we're getting closer. I'm watching the Y's. Ooh, there's Blinky. So below it is going to be to the left, and I hit enter. And above is going to be to the right, and I hit enter, and I enter through guess, and that is the best thing to see. Look at that 0. X is 600. That means this was factorable. And here's where it came from. It had to, because the 0 was 600. So now we can work backwards and say, well, this must have been a 13, because 13 times 1 would give me the 13r squared. And then I just have to figure out, if I take negative 420,000 and I divide it by negative 600, what would I get? And that's going to be a positive 700. And that was an educated cheat because we didn't want to try to look for those factors. I mean, there's so many numbers that can divide nicely, integers that'll divide nicely into 420,000. We could have been there all day. So our solution, r sub 1, is 600. This one, not so pretty, but we realize this is going to be useless anyway because it's going to be negative. And in the real world, that actually happens quite a bit with our quadratics that only one of them is going to be our solution. So now we need to go back and say, okay, what did they want? I mean, after all of this, did they want both speeds? Did they want just one? What was this question about again? Because we just did so much algebra to find that. And they want to know if the total trip took 13 hours, what was the jet's speed from New York to LA? And that was the original rate, the speed of the first trip. And that was our R sub 1. So all we have to do is write a little sentence here to say, hey, we found it. It's 600. So the trip from New York to LA, NY to LA, took, we'll figure this out in a minute, so many hours. We're going to put that down in just a second. Because what we know is the jet's speed was 600 miles per hour. No, it's not miles per hour. It is kilometers per hour. So now, we have this information that it's 600 kilometers per hour, and we want to know how long did that trip take, just so that we have all kinds of information. And again, they didn't ask us about this, but I could just see a follow-up question in your homework like this. And all we would have to do is say, well, it was 4,200 kilometers, and they traveled at 600 kilometers per hour. Well, if we divide those, we get 7. 7-hour trip. So again, we didn't necessarily need that part because it did just ask us about the jet's original speed. But because I know your homework is probably going to have the follow-up question in there, I wanted to make sure that we had that as well. That will be it for day 2, and we will have a little bit that we need to finish up from day 3.